Hi again, everybody. Welcome back. This is another example 1015, of where we're going to have to sum all the energy in the system at various different points. We're going to have to use conservation of energy. After all, we have this ball and a half pipe right here, and really the only force that we're dealing with is gravity. Gravity being a conservative force, we can sum up all the energy at all the different points. There's no values right here to plug in. We just need to predict. If you start the ball right here and you roll it down a side with friction, okay, now this is an important point. If it has friction, it means that as the ball rolls downwards, it rolls down here, or I should say as it moves downwards, the friction between the ball and the surface itself is going to cause it to roll. All right, so it's going to do like that down to the bottom. All right, the friction is really not, say ideally, the friction is not causing any energy to be lost. Rather, the friction is simply causing the ball to turn as it moves down. So it's got linear velocity as well as rotational velocity as well. However, as we go back up, okay, as the ball goes back up, and let me do this in a different color right here. I'll do this in green. All right, the ball is going to be moving up like that, and it's still going to be spinning. But think of it like this: if there were friction on the side, which by the way, on this side there is no friction, so it can sort of spin around and it can keep turning, even though it's maybe not turning at the same rate that it's moving against the surface. So it's sort of skidding on the way up. If it's a frictionless surface, and as it moves up, the ball continues to spin, even though linearly it's slowing down. Does that make sense? All right, so this right here, the ball starts at rest. It's not rotating at all. As it moves down and as it gains linear speed, it also gains rotational speed. But here, as it goes up, it loses linear speed, but since it is frictionless, and that means even though it's slowing down linearly, it's not slowing down rotationally. So it's still going to continue to rotate as it goes up to whatever level right there. Okay, so even if it goes up to this one of these points, and we're supposed to pick which point it's supposed to go up to, one of these points, and then stops moving linearly, it's still going to be rotating because there's no friction between the ball and the surface in order for it to slow it down. Does that make sense? Okay. So we need to simply predict, as you roll it down from here, which height is it going to reach? Is it going to reach the original height, right here? Is it going to go less, or is it going to go to a greater height than it was released from? All right, well, let's start by summing all of our energies. In fact, let me shrink this down a little bit so I have some more space. I really have to have some more space on the left there, but I want to just mark this up kind of right here. All right. So let's mark the initial energy. I'm not even going to call it initial. I'm going to call it energy 1. So this is point 1 right here, point 2, and point 3, wherever point 3 happens to be. Okay? Where is the initial energy, or what initial energy does it have at point 1 right there? Well, it's got potential energy due to gravity, right? And that's mgh. Okay? So that means at any other point, it has to have the same amount of total energy as it has right here. Whatever the mass of the ball is and whatever that height is, we can figure that out. But we're just using general terms right now. All right, at point 2, what kind of energy does it have? I'm going to write that at the bottom right here. Energy at point 2. Well, it has rotational kinetic energy. Okay, and it has linear kinetic energy. And we know that's 1/2 mv squared, and that's 1/2 I omega squared. Okay? So, if this had friction on this side, basically you'd have the opposite happening as what happened down here. It would start from rest, it would accelerate linearly and accelerate rotationally, and then it would decelerate linearly and decelerate rotationally as well, so that we'd have the same amount of energy at the top right here at point 3. But at point 3, the energy that it has is going to be, well, what kind of energy does it not have? Well, wherever it reaches its highest point right there, it no longer has any linear kinetic energy, right? Linear kinetic energy is going to be 0. But it still has, I'm going to have to draw this vertically. No, I'm not. I can do this. All right? It still has rotational kinetic energy. All right? It's still rotating because of this frictionless surface. Even though the ball is slowing down linearly, it's not causing the ball to slow down rotationally, and so it still has that rotational kinetic energy. But it also has what? Well, it's risen up some sort of height, right? If this was our original height, we'll call it height 1 right there, then that means height 3 right here is going to be some point that it raises up to. And that's really what we're asking. What is that height 3? Is that going to be greater than, equal to, or less than height 1? Well, that's mu g, or ug right there, our potential energy due to gravity. Well, let's use some logic right here. Instead of math, just use some general logic to figure this out. If it originally has, all of its initial energy is potential energy due to gravity, right? It's going to be at a pretty high height right here. So it's the same total energy. None of it is potential anymore. It's all rotational and linear kinetic energy. And as it raises up to this final height, it has gravitational potential energy, but also rotational kinetic energy. It is still spinning, even though linearly it has come to rest. So therefore, our potential energy due to gravity at 3 has to be less than the potential energy of gravity due to 1. Why? Well, because you've got this potential energy due to gravity at 3, plus it still has this rotational kinetic energy. So I probably should have written it like this. Ug at 3 plus k rotational at 3 equals potential energy of gravity due to 1. And if we're solving for this potential energy due to gravity at 3 right here, we're going to have to subtract this kr over, and that means that the 3 is going to have to be less than 1 right there. So 3 is going to have a lesser height than 1 because part of that energy that it originally had that was potential is still wrapped up in rotational kinetic energy because we have this frictionless surface right here. All right, so that's kind of the logic behind these types of problems. We're using still conservation of energy, but we need to account for all the energy and know what an object is doing so that we can determine how much of the different types of energy that it has. So that's it for example. What example is that? 10, 15. No actual values to put in, but some ways of thinking about these types of problems so that we can predict the types of energy and the amount of energy that it has at any one point. Thanks for following along. I'll see you on the next one.